Lecture. Here we go, folks. We're getting into the spectroscopy. All right, so this is kind of going to be a little all over the place with respect to the chapter and section that we are in the book. The book kind of divvies up everything on spectroscopy in kind of a weird way. So that's why you see that it says select content from chapter 13 here. And so that's going to happen with some of the other chapters. So I apologize for that. I'm going to try to keep it as organized as I can. But I wanted to put together like a custom set of topics that I think fit nicely together. Okay. Excuse me. So the first thing I want to get into is a little bit of review. So hopefully this all looks familiar. I know we've talked about this in Chem 361, but also in your other classes. Okay. And so what I want to describe is simply the phenomenon of light passing through an absorbing sample and then going on and detecting that light. Okay. So let's label a few things here. So I0, this is what we call the incident radiation, and that could be ultraviolet, visible, infrared, right? So we're just going to say generically that this could be any incident electromagnetic, let's put that qualifier in, EM radiation. Okay. So when we have an absorbing sample, the intensity of this light will decay exponentially through the sample as it passes through, right? So if we imagine looking at this as a wave coming through, right, we will see this exponential decay of light intensity. And if the optical depth is sufficiently small enough, then light will make it out of the other side. Okay? If the optical depth is sufficiently large, then that means all of that incident radiation has been absorbed and we won't detect any. Okay? So this is why we typically look at low concentrations in spectroscopy so we can make sure all of our incident radiation comes through so that we can detect it. So, and often I draw a little profile of an eyeball right here to symbolize a detector. Okay, so that is an exponential decay, right? So by definition, optical depth tau is given as the natural log of the ratio of the incident radiation to the transmitted radiation. Okay, so let's define that. So that's the transmitted EM radiation, defined by I. Okay, so it is an exponentially decaying function. So to me, it makes good sense to use the natural log. And of course, we could define the transmittance T as the ratio of the transmitted EM radiation over the incident radiation. And that will also have an exponential function. That transmittance can be written as the exponential of the negative optical depth. And of course, as you might imagine, if we supply, right, if we write that in, e to the negative natural log of I naught over I, then the e to the natural log cancels that out, and the negative sign makes these flip, and that's where we get this to be I over I naught. Okay? So why we use log base 10 for absorbance, I have no idea. Maybe just to confuse you poor students even more. But if I was writing the damn equations, I would have kept absorbance as a natural log relationship because it is a naturally exponentially decaying function. In any event, I don't write the rules. So absorbance by definition is given as log base 10 of IO over I. And of course, certainly we could say then A is the negative log of T, the transmittance. But what that means is if I want to relate absorbance to optical depth, then I have to change my base. And the way that I change my base is by taking the log base E of 10. And that will convert that log base 10 into a log base E. Okay? So we can use the Beer-Lambert law, Beer's law, as we know more colloquially. But the Beer-Lambert law can be written for optical depth or absorbance. So when it's optical depth, we typically will report we will typically report concentration there. Remember, in molecules per cubic centimeter. Okay, so our path length is always given in centimeters. And so what this means, this sigma, if you recall from Chem 361, this is called our absorption cross section. And that's given as centimeter square per molecule. And it's very much a cross section, the way that this is viewed. So in other words, a small cross section will lead to not very much light being absorbed, right? If I imagine now a wave coming in through here and I've got a small cross section, then I'm going to be able to transmit through the other side, okay? But as you might imagine, if we were to have a very large cross section, that large cross section we could really think of as like a sponge for all of our photons. A large cross-sectional absorption area will suck up all of those photons and none will be left to transmit. Okay? So that is the natural way of looking at Beer's law in the base E. Of course, the way that you've all been looking at Beer's law, which is the way we do it in chemistry, is the base 10 measurement, where now my concentration here is expressed in molarity, mole per liter. My path length is still given in centimeters, and now that means my absorptivity coefficient, so I'll just say, I'll write that as absorptivity coefficient. So that's going to have units of, it's got to be reverse concentration, liter over mole, and because the centimeter is there, centimeter. And now, of course, this quantity, the absorption coefficient, we know that we normally empirically determine that coefficient, right, by making standard curves and so on. But if we wanted to relate that absorptivity coefficient to the actual physical parameter, the cross section, then we'd have to consider this base E. Okay? And so if I do the algebra here, assuming that my concentrations are the same, right? We know that we have different concentration units, so there is going to be a factor of like Avogadro's number and the conversion of cubic centimeter to liter. So if we ignore those conversions, okay, then I can write that the cross section sigma, right, and I have to multiply natural log of 10 up there, and the natural log of 10 is 2.303. So I'll write that down, okay? So that means the absorption cross-section equals 2.303 times the molar absorptivity coefficient, assuming that you've also got equivalent units, right? So that 2.303 factor is just for the base E to base 10 conversion. Okay, so hopefully that was good review. And all forms of spectroscopy generally follow this mantra, okay? At least all transmission spectroscopy techniques. Not all spectroscopy techniques are transmission techniques, and we'll talk about those as well. So, for example, one type of spectroscopy that is not a transmission-based spectroscopy is a reflection-based spectroscopy. So there are several methods that take advantage of reflection as opposed to transmittance, okay? And in those techniques, right, I would have a sample of interest Okay, so that's the sample that I want to take a spectrum of, and I would shine some incident radiation, some incident EM radiation, and it would be reflected off the surface, where then I use a detector to detect that reflected radiation. And of course, as that incident radiation is interacting with the sample, it might absorb, or the sample might absorb some of that light, and so the reflected component will have some of those wavelengths absorbed. Okay. So just as a reminder, so our law of reflection says if I have a perfectly atomically smooth surface, this is technically got to be atomically smooth, which there's no such thing. But if there were, then our angle of incidence would match our angle of reflection perfectly, right? So we have the normal line here. So that's the normal line, right? That makes a 90-degree angle to the surface. And even though there's no such thing as an atomically smooth surface, we can still get some really nice, what we call specular reflection, right? That's this perfect angle of incidence matches angle of reflection. Even a non-atomically smooth surface, like a mirror or an optic, will still give us some very reasonable specular reflection, okay? So for example, here's a picture of a lake. That is definitely not atomically smooth, right? But we can see this beautiful mirror reflection. That's called specular reflection. So anytime we see that mirror reflection, right, where the angle of incidence matches the angle of reflection, that's called specular reflection. And like I said, even if we don't have something that's atomically smooth, we will still get a very decent amount of specular reflection. Okay. Now, when something is not atomically smooth, so I'll call this a real surface, we get what's called diffuse reflectance. And as you can see with this picture here, we draw, so the dotted line is still a normal line. So we make a normal line about where each photon is reflecting. And so within each one of those, we will have a specularly reflected component. However, because the surface is rough, right, and none of those leaving incident reflecting, none of those leaving photons will have the same angles as each other, then we don't get a mirrored reflection, okay? So no mirrored effect. So what that means is with this lake picture, as the wind picks up in the day, as the water becomes more choppy, we're not going to have that beautiful specularly reflected light coming off the surface. It's going to be diffusely reflected. And the diffusely reflected light will just look like a normal lake surface, okay? And so if you've ever looked at a roughed mirror, or like an older mirror that might not be as smooth as it used to, you will note that there is still some specular reflection going on. But there is a degradation of quality of the mirror image, and that's due to the diffusely reflected components, okay? All right, so moving on. So refraction, we haven't gotten to talk about this a whole lot, and this is really important for spectroscopy, right? Because as you note from this picture right here, our beam might be transmitting through one type of medium, perhaps air, then it transmits through another type of medium, maybe water, or first of all, glass, right? The glass surface of the cuvette, then the water, then the other glass surface of the cuvette, then back to air, okay? So all of those have different angles, or excuse me, different indices of reflection. That's what these ends are, okay? And so what that means is in spectroscopy, it can be quite chaotic as our beam is transmitting through several different media. And I'll talk about how we overcome that momentarily. But there's two important things to note. The critical angle and the total internal reflection angle. So the critical angle is this really cool optical illusion where a beam of light coming through, let's say water, is reflected at the surface and doesn't make it out. So what that would appear if, let's say, I had an object down here, right? And we'll put a detector up here, maybe an eyeball. And perhaps I had an actual object. I don't know. I'm just going to draw like a rock or something. Like, suppose I had some kind of random, rock or whatever, a precipitate in there. If I was looking at this critical angle, it would appear that it was not there, right? The light coming off of that surface does not make it out of the medium, and it would appear as if the object were not present. So that's what's called an optical illusion. Okay? And similarly, the total internal reflection would give us a similar effect. And what's really special about the total internal reflection is our angle of incidence matches our angle of reflection. Okay? So this will be really important as we look at other types of spectroscopy where we can actually bounce a beam of light through a total internal reflection just straight through a medium, right? So without letting it pass up and out into the air, where we can literally bounce a beam of light right through one medium through its total internal reflection angle, okay? And the advantage of this, it gives us a long path length, right? So if we think about it, our Beer's law says epsilon times concentration times path length. And if you had either a low sample concentration or a poorly absorbing sample, your absorbance would be quite low. So a couple ways that we could improve that would be, well, to increase the concentration for one. But if you can't increase the concentration, we could increase the path length. And that will increase the absorbance on a low concentrated sample. So for example, right, if I'm just passing a beam straight through this material, right, we'll call that path length number 1. But rather, if I can bounce a beam through its total internal reflection, right, and if I design this experiment correctly, I will get multiple total internal reflections as this light is coming through. And so this means L2 will be greater than L1, and I will improve my absorbance or my sensitivity to the material that I'm trying to take a spectrum of. Okay? So moving on. So diffraction, so we talked about this with electron microscopy. And so remember, the big learning goal here was the smaller is the barrier, the wider is the angle that is diffracted. Okay? And typically, this is taken advantage of in spectroscopy. But generally, this is done in spectroscopy to provide a focus, right? So we use a special opening size, okay, to provide, let's say, some more focus to our beam. So we often call that a collimated beam. So this would be collimated. This would be divergent. So typically we want a collimated beam in spectroscopy, right? We want a nice consistent beam at a similar angle for consistency. So we know exactly how many photons we're shining on our sample, okay? So let's keep going with this. So I'm going to describe a technique that we use, which is called a monochronometer. monochronometer. I still have to say that slow to this day. Monochronometer. Okay. So this is a way in which we can take advantage of specular reflection as well as diffraction to create light of any wavelength that we want, okay? Or to select a wavelength of light from an incident white light source, okay? So if we go back to the basics, so if we shine light on a surface, of course, we will get the specularly reflected light, right? Where the angle of incidence matches the angle of reflection. However, if we put some grooves on this surface, so zooming into this grating right here, they're actually not a smooth surface, but rather they have very regular grooves, okay? Typically indicated by this distance d. So this distance d is giving me the center point of this groove to the center point of this groove, okay? Then I can create a diffraction pattern, all right? And so I'm not going to get too crazy detailed into the math. The way this works is to get a diffracted wavelength, we have to have whole number integers. So this n times lambda, that means a whole number integer wavelength. So for example, if I want to get a wavelength of 500 nanometers, okay, I could use any integer of that 500 nanometers. So it could be 500 nanometers for n is 1. It could be 1,000 nanometers. It could be 500 meters if we wanted to. That would be a huge grating, right? But as long as it's a whole number integer of the wavelength in question, and particularly the CB plus BD length. And so like I said, I'm not going to derive this. So this gets into just geometry. It's a geometrical derivation. But the way this works, the C plus B and B plus D distance must be some integer wavelength, right? So I'll try to draw that the best that I can, you know, maybe something like that, right? If I were to unravel that full distance, I need it to be a whole integer wavelength. Then whatever that value is, whatever that wavelength is, that is the wavelength of light that will come off given the incident angle I, and of course the incident angle R. And if you think about this for a second, okay, the way that this works out, we get this pattern where lambda decreases as we go this way. So lambda is, backwards. Lambda is decreasing as we increase that angle of reflectance, which I've always found is kind of counterintuitive. You would kind of expect as that angle of reflectance is increasing, you've got a longer path for a longer wavelength, but it's all about the integers. It's all about the integer wavelengths, okay? And so what ends up happening for a given constant angle of incidence, okay? So we don't have to change that constant angle of incidence. We will automatically get several different wavelengths that satisfy this equation, okay? And so typically the way that this works now, if I draw my detector up here, I don't want to detect the specularly reflected light. I want to detect the different colors. This grating will pitch and roll to give us those angles that we want, right? So that grating will actually move, so it moves the desired wavelength into the path of the detector, okay? So that gets us into describing the two main types of spectroscopy, the Fourier transform technique and the dispersion technique. So what I've been describing up to now is the dispersion technique. right? Typically UV vis. Okay? So in dispersion spectroscopy, it's the measurement of the absorption of light of a single or narrow range of wavelengths one at a time. So these wavelengths are typically scanned one at a time using a diffraction grating, right? So we would have our diffraction grating right here. We would have our incident light coming in, and let's draw a couple of different colors right here. Okay. And we would have our sample perhaps somewhere right here. And we would actually rotate that monochronometer, one angle or one wavelength at a time, whatever our resolution is capable of doing. Okay, where our detector is now going to be on the other side of the sample, right? And so we would do that one at a time, and our spectrum would be put together by scanning through all of those wavelengths. Okay, so again, that is pretty much UV vis. UV vis is pretty much exclusively dispersion spectroscopy, and that is typically done because these diffraction gratings can be made quite small, and we can just use a regular ordinary white light source. So it really is a matter of convenience based on the wavelengths that we're using. So for example, if we wanted to use dispersion spectroscopy for FTIR, we could do it, or for infrared rather. So we'll say visible, ultraviolet visible. We could absolutely do dispersion spectroscopy with an IR source of light. It was done before the FTIR existed. However, that is not convenient at all because of the size of the wavelengths. Remember, IR wavelengths are much bigger. The grating would have to be huge. It would have to be so huge that you couldn't conveniently use the spectrometer on a bench top. I mean, these gratings would have to be approaching several meters in size to use, FTIR or NMR, particularly if we wanted to use a dispersion or a grating for the radio waves associated with NMR. They'd have to be several meters in length. IR, perhaps, several dozen centimeters in length for the grating. It can be done, but it's not very convenient. So the Fourier transform technique, so Fourier transform is a mathematical algorithm. Okay, so we'll write that down. Mathematical, assuming I can spell algorithm. I probably didn't spell that right, but that's okay. So it's a mathematical algorithm that converts the time domain to a frequency domain. And that's convenient. And by domain, I'm talking about my range of values. And so that's convenient because if we think about things in terms of frequency, we can easily convert that frequency into a wavelength, which is what we're interested in spectroscopy. Okay? So in the FT technique, all of the wavelengths are measured simultaneously at very high spectral resolution. And what I mean by spectral resolution is the difference in wavelength that we can measure. Okay? So in this dispersion technique, if my resolution, if let's say my delta lambda were equal to 1 nanometer, then that means each time I pitch that grating, I'm capable of resolving 1 nanometer from the next. So for example, I could see a 532 nanometer photon. Then I could see a 533 nanometer photon. Then I could see a 534. Well, as it turns out, that 1 nanometer, which might sound small at first, is actually humongous. Because that 1 nanometer in terms of vibrations or rotations is humongous. It's way too big to be useful for the very small energy spacings between levels that we need for the infrared or even the microwave technique or even the NMR technique. All of those techniques have insanely small energy level spacings. So we have to have a very specialized way of having high spectral resolution, okay? And so we do that by using this Fourier transform. And also there's a special instrument we have to use the Fourier transform, which is called the Mickelson interferometer. All right. So I'm going to describe this very briefly here because in your Spec 3 assignment, we're going to dive into Fourier transforms and interferometry in full glorious detail. So only a brief background for now. Okay. So the way this starts, here we have our sample, and here we have our detector, and here we have our source lamp. And that source lamp is an IR source of radiation. And so typically it's just a hot piece of metal. It's that simple to make an IR source of radiation. It's literally just a piece of metal, and a bunch of electricity is pumped through it resistively to get that piece of metal hot so that it's glowing infrared wavelengths. That's it, okay? So it's just a glowing metal rod. And so there is a little bit of orange and yellow that comes off of it as well, but predominantly infrared. So it goes through a convoluted beam path, okay? So you can see a set of mirrors. We'll focus it on what's called a chopper mirror, or often what's called a beam splitter. Two synonymous. They're not, a chopper mirror and beam splitter are slightly different, but they give us the same function, and that is they will split the light based on its angle where it's interacting with the mirror, okay? So for example, in this mirror, it allows the light to pass straight through, okay? Light is also reflected at this angle as well, hits this fixed mirror, bounces back and transmits through all the way through the sample, okay? And similarly, when this light that transmits through the beam splitter hits this vibrated mirror, or sometimes we just call it the moving mirror, it will also come back and hit this angle and come down through the sample, right? So like I said, it's a convoluted beam path where there are lots of opportunities for destructive interference and constructive interference. And that is precisely how the technique works, okay? So this is an interferogram. So this graph right here, interferogram. And this X scale right here is the distance that this mirror moves, all right? So there is some center point right here given by what's called zero retardation is often the word we use to describe how this mirror moves. Because it's vibrated, so the mirror is vibrating back and forth, okay? So we often call that modulation or retardation, the way that the mirror moves back and forth. So at the 0 point, and I know it doesn't look like it on this figure, but at the 0 point right here, the F distance equals the M distance. And so that will give us maximum constructive interference, okay? And as this mirror moves, you can see there's huge sweeping destructive interference where it goes all the way down, and then constructive interference where it comes back up, and then destructive interference, and so on and so forth. And you also notice that it's symmetrical about the other side of the mirror, right? The mirror is moving back and forth this way about this center point, okay? So it will be a two-sided interferogram. And so what this ends up doing, because our IR source is broad, so it has a whole plethora of different wavelengths. Those are all interfered with constructively and destructively in different ways as this mirror is vibrating back and forth. And so what this does is it creates insanely high spectral resolution. Because as you can see each of these data points right there, right? Each one of those data points will give us a unique combination of wavelengths that make it through and onto the sample. And so by the time you've scanned through all of your wavelengths, and that's achieved by literally just moving this mirror back and forth, you will have passed through every single wavelength available from this lamp at insanely high spectral resolution. The Fourier transform is then the mathematical algorithm that converts this signal right here into a spectrum. That's right. And so we have to view this on a time domain. Even though it's showing this as a distance, this moving mirror has a certain velocity that we program in the spectrometer. And that velocity multiplied, the distance that the mirror moves divided by its velocity will give the time domain of this. The Fourier transform converts that into an actual spectrum. And when I was an undergrad, I used to think that process was just like magic. How you go from this figure into an IR spectrum, it's kind of amazing. It's what we're going to be doing in our Math 3 assignment. So that should be very cool. Okay, so I've been talking quite a bit. So I'm going to break this up into another lecture. So I'll pick up with this in the next one. Alrighty, folks.